In this screencast, I'd like to discuss multiple regression. Multiple regression allows us to isolate the effect of one independent variable on the dependent variable while controlling for the effects of other independent variables. Just to review in this chapter, when we used bivariate regression, we found the following. States with higher levels of education have higher turnouts than do states with lower levels of education. Another separate bivariate regression produced the following result. Battleground states have higher turnouts than do non-battleground states. But now here's the problem that multiple regression can address. The two independent variables are themselves related. Education and battleground are related, perhaps surprisingly. For example, battleground states average 66% on the education variable, meaning that 66% of the residents on average have a college education. This compared with only 58% for non-battleground states. So what this means, the complication here is when we compare battleground states with non-battleground states and compare their turnouts, we're also comparing states that have higher levels of education with states that have lower levels of education. So is it being a battleground state that causes the turnout, or is that effect being confounded by the fact that we have not controlled for education? Just to repeat, so when we compare battleground states with non-battleground states, we are also comparing high education states with low education states. And to the extent, as we know, that higher education states have higher turnouts, then it might be the education effect that's detracting or adding or confounding the battleground effect. Here's the solution. Multiple regression. Multiple regression is a sophisticated version of controlled comparison analysis. Multiple regression produces a partial regression coefficient for each variable. Now, what's a partial regression coefficient? A partial regression coefficient estimates the mean change in the dependent variable for each unit change in the independent variable, controlling for the other independent variables in the model. Here's the general form of multiple regression. As always, alpha, or a hat, is the estimate of the dependent variable when all the independents are zero. The key difference here is B1 will estimate the effect of x1 on y, controlling for all the other variables, x2, x3, x4, x5 that are in the model. It partials those effects out and gives a, I guess you might say, a pure partial effect of x1. Same for x2 and all the other independents. For the problem at hand, here's the model we want to estimate. We want to estimate turnout in the states as a function of college degree or higher plus battleground. So in this formulation, B1 will estimate the effect of education on turnout, controlling for differences in states in terms of if they are battleground states or not. And similarly, the dummy variable battleground will estimate the effect of being a battleground state on turnout, controlling for differences between states in education. So we're going to isolate the effects of each of these variables and estimate their effects. Here are the estimates. If you're reading over here, education B1 is 0.55. So for every 1 percentage point increase in college graduates, turnout goes up by, on average, 0.55 of a percentage point. You may recall in the bivariate analysis, I believe the effect of education was about 0.6, but that was before we controlled for the battleground factor. Doing so reduces the effect of education, although it remains significant. The standard error is relatively small compared to the coefficient. We have a large t-statistic, 3.52, and a small p-value. So we would say yes, education continues to affect, its partial effect is significant. Same for battleground. The dummy variable here, the estimate returned is 7.63 points. So on average, battleground states have turnouts that are 7.63 points higher than non-battleground states, controlling for education. You may recall in the bivariate, I believe that effect was a little bit over 8 points. But that effect didn't account for the fact that battleground states have higher levels of education than non-battleground states. Again, we get a real manageable standard error and a large t-statistic and a p-value that invites us to reject the null hypothesis. A final note on this, The adjusted R-squared multiple regression tells you the effects of, it tells you how completely all the independent variables in the model explain the dependent variable. So we have a nice R-square here of 0.364 that tells us of all the variation across states in turnout. We can explain about 36% of that variation by knowing a level of education of the state and whether or not it had battleground status. Just to repeat, to emphasize here, education, controlling for battleground. For each 1 point increase in education, turnout increases by 0.55 of a point. In the bivariate, education effect was 0.6 of a point. Battleground, controlling for educational differences across states. Battleground states have turnouts that are 7.63 points higher on average. And again, in the bivariate, we didn't control for anything. We got an inflated estimate of the effect of battleground, because that original estimate also included some effect of educational differences on turnout. But now we've taken that out. We've controlled for that. As we saw, the t-stats, standard errors, p-values tell us that each variable has an independent significant effect on turnout. Adjusted R-square in multiple regression tells us how completely all variables in the model explain the dependent variable. By knowing two things about states, their level of education and their battleground status, we can account for 36.4% of the variation across states in turnout.